3D moment example. This is a problem, it's a flag. And this is the Z-axis is the flagpole. And we have got an X-axis out here, and we have got a Y-axis down there like that. And this flag is held up. Here's the origin. Point A is right here at the bottom of the flag. And then we've got a point B out here on the Y-axis, and we have a wire that goes from A to B, and there's a force acting along that wire or rope. This is the force that goes to point B, and it is 780 newtons. There's actually another wire that goes off to another point C over here, and it has a force in it. We're not actually going to use this, but it has a force in it of 420 newtons. And those two forces are, I guess, holding the flag up so it doesn't tip over. We put some dimensions on here. We have got 6 meters up, and we have got 2.5 meters over there to point B. And all the problem actually asks is to find the moment that FB causes about point O. Okay, great. So it's a 3D problem. I'm going to solve it 2 different ways. Okay, I'm going to pretend for a minute that I can't visualize anything to do with moments yet. I'm just new at this and I prefer math. And so I'm going to first solve it by using moment is equal to R cross F. If I can write those vectors, I can take that cross product, I will get the right answer. A couple ways to solve it. My position vector has to start at point O. It can go to anywhere along the line of action of that force. So pick an easy point. I suggest position vector from O to A. That position vector has no X component. It has no Y component. It is simply you go 6 meters up in the K direction. If you didn't like using A and you wanted to, you could do a position vector from O to B. That'll work as well. It's a 2.5 meter vector in the J direction. So either one will work. We also need a vector for our force. The force goes from A to B. So let's start with a position vector from A to B. To get from A to B, I've got to go 2.5 meters in the J direction minus 6 meters in the K direction. First, convert that into a unit vector. So to do that, I have to divide out the length. The length is square root of 2.5 squared plus 6 squared. And so once I divide out that length, I get 0.385J minus 0.923K. They have to be both numbers smaller than 1 because this guy has to have a total length of 1. So they have to be 2 decimal numbers. So when you square them and add them up, you get 1. Then my force, B, expressed as a vector, is going to be 780 newtons times 0.385J minus 0.923K. I like to multiply it out at this point. I get 300 newtons in the J direction minus 720 newtons in the K direction. So I have a force vector and I have 2 different position vectors I could use. I could either use OA or OB. They'll both work. So my next step is to actually do the moment. So I'll set it up as a cross product. I've got I, J, and K. Let's use position vector. Should we use O to A? 0, 0, 6 meters. I like to write my units down and make sure I don't mess anything up. And then I write down 0, 300 newtons minus 720 newtons. The negative sign is super important. My trick for how to calculate this is to copy, paste, and then I'm going to do these 3 times each other. Well, that's a 0. These 3 times each other, there's another 0. And these 3 times each other, there's another 0. Now I go the other direction. K times 0, so minus 0. Oh, this one's finally not 0. Minus I times 6 meters times 300 newtons. And then this last one is J times 0 times minus 720 minus 0. So my answer is minus 1800 Newton meters. You could say in the I direction or about the X axis. This is my moment as a vector. I want to go back and solve this a different way. Well, and the different way isn't I'm just going to plug in ROB instead. You could do that. Instead of 0.06 meters here, you could have done 2.50 meters. You could have done ROB. I want to solve it using scalars and visualization. What I want to think about here is this force vector has got 2 components. It actually only has a J and a K component, but this scalar analysis also works if it has all 3. It has got a component in the Y direction that is 300 newtons. It has also got a component in the Z direction that is 720 newtons downward. That's what the negative sign means. Now, if I want to find the moment that this force altogether causes about 0.0, I can simply break it down into its components, which I've just done, and analyze the moment that those 2 components cause about 0.0. I can do that using perpendicular distances. So look at the 720 newtons. It is pointed right at 0.0. There is no perpendicular distance. For there to be a perpendicular distance, it would have to be off to the left or off to the right. It would have to be away from the origin, but it's pointed right along the Z-axis toward the origin. So that guy contributes not at all. On the other hand, this this 300 Newton force, it is a perpendicular distance of exactly 6 meters away. So guess what the moment is? This is using my scalar analysis. It says that the 720 Newton component causes no moment, about O, but the 300 Newton component is 6 meters away, and that is a perpendicular distance, perpendicular. So that means that the total moment is going to be 300 newtons times 6 meters. It's going to have a magnitude of 1800 Newton meters. Now we got to figure out what axis it's acting about. So here's where your right-hand rule comes in. Start at point O, your fingers go straight up the z-axis to the force, and then they curl toward the positive y-axis. Curl. When you do that, using your right hand, your thumb should be pointing back toward the negative x-axis, back in this direction. So we say that this force creates a moment about, acting about the negative x-axis. So this moment acts about the negative x-axis. Or we write it as minus 1800 Newton meters I, which is what we got before, right? 1800 Newton meters I. There's your moment vector. If we were to go back and rework this example using FC, from A to C, that force actually has components in all three directions, which we could break out. It's got a vertical component, it's got a horizontal component in the x direction, and it's got a horizontal component in the y direction. Well, same analysis, the z component, downward component, that will not cause any moment about point O. This horizontal one acting in the negative y direction, start with your fingers at O, they go up the z-axis to where the force acts, and now curl them toward the negative y-axis. Your thumb is now pointing in the positive x direction. So this guy right here causes a positive moment about the x-axis. This one out here that's pointing in the x direction now, start your fingers at O, they go up in the z direction, they curl out toward the positive x-axis. It's actually going to cause a moment about positive y-axis. So if I were to do the same problem for FC, it's going to be really similar analysis, but when I'm done, my moment will actually have two components. It'll have a component about the x-axis caused by force in the y direction, and it's going to have a moment about the y-axis caused by the force component in the x direction.